he said, the student said Bard seems to be regressing, and I haven't noticed that, but I certainly noticed it with OpenAI, and everyone else did too. And OpenAI explained that it was costing them too much to run OpenAI. So they made it use less CPU power, and everyone noticed the quality of the answer went down by quite a lot. However, I've seen a lot of news in the last couple of weeks that people have developed much more efficient AI algorithms, like 100 times more efficient. So also, OpenAI's traffic has been dropping and dropping. They're worried about their stock price and their company success. So OpenAI was the first, but they don't seem to be competing successfully against the wave of alternatives that are coming out. So they may not be the big winner here in the long run. Anyway, all right, so we'll talk about the types of training models that are out there. I was very pleased to get this information. We've already, of course, used several training models, but if you read the book and follow these, they say, here we are using something called linear regression, but we aren't really explaining what it is. We're just taking one of the standard models and seeing it go to see what it can do. And later on, we'll get into the details of how it works. And that's what's happening here. So we'll talk about linear regression, gradient descent, and polynomial regression, which is a very wonderful trick to fit a curve without having to fit a curve, and then ways to measure it. So linear regression is a very simple activity, very important. You have a series of points. Let me get down, should be a picture there. You have a bunch of points like this, and you want to put a straight line through the points. Very simple. And this problem has been solved for a long time. Simple ways to do that, simple statistical procedures. That's linear regression. And one good thing about it is you don't need to hunt through a bunch of steps. You can just go to a closed form model for a lot of versions of this. So there's two ways to train it. The closed form equation is the one I've known for a long time. Before you use computers to do it, you would just directly compute the parameters. From the data points, there's a way to mathematically determine the best line to go through those points. There's various ways to express the formulas. They're just simple formulas to calculate it from the points. So it's very fast, very efficient, and like I say, we used to do it before there were computers. Then gradient descent is the iterative process. If you have a more complicated situation where you cannot mathematically calculate the best parameters with one move, then you guess and improve it and go through a series of epochs, like quite a few of our demonstrations have been, where it has to try hundreds of epochs to get there. Is that what your demo with TensorFlow and Google? Yeah, the TensorFlow and Google collab we've done are fitting models like this, and most of them are gradient descent, the one with many cycles. Yes. And so what this does, you gradually tweak the parameters to minimize a cost function, and there's different kinds of gradient descent we'll talk about: batch, stochastic, and the one in the middle, mini batch. So linear regression, there was an example in the textbook they talked about where they're going to calculate life satisfaction from your wealth. This is certainly a standard American Western idea that the way to make people happier is just give them more money. And by the way, I think the psychological studies show this is true if you think about poverty. When people are really poor, that makes them miserable. When you get them up to enough money to afford, a reasonable place to live and some food and stuff, then they're a lot happier. Money beyond that point doesn't continue to make them happier, and that's why I often talk to students that envy power and wealth and say, it doesn't look to me like Elon Musk is very happy. I don't think you need to get all that rich, but it certainly is true that moving from a desperately poverty-stricken situation up to sort of middle class does make you happier. So anyway, that's one simple model. In general, the model looks like this. You have these theta parameters, and you have these inputs of some real measurement. So you have measurements of some kind of your input, x1, x2, and x3, and you just have a offset and then a slope for each of those things. That's a linear model in multiple dimensions, where you have inputs, however many you want, and you have that many parameters plus one. And since it's a straight line, the math is very simple, and you can do it very efficiently. So you have a cost function, and here's the traditional cost function. It's been known for centuries. This is the one that is the most mathematically easy to use. You take the difference between the prediction from that model and the real value, and you square it. And you sum up the squares, and then you can divide by the total number to get a mean, if you like, and that's called the mean squared error. This is a classical way to measure how wrong you are, and if you just want to minimize the mean squared error, that can be done analytically. with the normal equation, and they express it in a book using tensor mathematics. And if you don't know enough math to completely understand this, you don't really need to worry. The point is just that is a mathematically solvable problem, and you do it by taking the matrix transform and multiplying it by the matrix, calculating the matrix inverse and multiplying it by the matrix transform. And the point is all these are simple mathematical operations involving integer arithmetic that you can easily do on a GPU, which is why this kind of thing can be done really fast on a modern computer. It's just a matter of multiplying a lot of little terms together and adding them up. You don't have to go through steps. You can just get immediately to the one that will minimize the mean squared error. So you can do it here. You calculate your prediction, and that's what you'll see. What you ought to see, the red line is the one with the lowest squared error going through those points, and it agrees with your intuition. That does look like the line that goes through the points nicely. So if you consider, you can figure out how much computer time this will take. Calculating the matrix inverse of this thing turns out to be a problem of approximately n squared. So the overall thing is between n to the 2.4 to n to the 3. This order is a computer science term where you figure out not exactly how long it will take to do something, but how much it changes as you make the problem bigger. This is the main way you measure a hard problem to an easy problem in computer science. You consider what will happen when you have a large problem. So this is basically the number of points you're feeding in. And so if you have 10 points, it takes a certain amount of time. If you go to 100 points, it'll be 10 to the 2.4, 10 to the 3 times more. So if it's 3, then multiplying the number of points by a factor of 10 will multiply the time by a factor of 1,000. And that's what's really important, because real problems typically have a lot of data coming in. And that's what you worry about. So the training is going to be relatively burdensome if you have a lot of points. For you consider something like the large language model that train on all the worlds they can find on the internet, that's an enormous data set. But once you've trained it, and studies, I've heard people say that training the large language models like ChatGPT costs something like $40 million of computer processing time. But once you've trained it, prediction is really fast. Using the model is just this calculation here. Now training it is this matrix inverse stuff, which is on the order of the size of the model squared or cubed. But using it is just this. It's just adding up a constant times each of the value. This is just one vector multiplication, if you like. All you do is, if you have 100 parameters, you just multiply each one of them by the constant and add them together. So this is a really fast operation. Actually, that's the error, pardon me. Here's the prediction. That's the prediction. That's all you have to do to use the model. So once a model's been trained on some big, expensive cloud machines, you might be able to run it on a cell phone just to get the answer, and that's certainly the case with large language models. All right. So that's nice. Yeah. All right. When you can't use the closed, sometimes this closed form thing is not sufficient. One is if there's a large number of features or too many training instances to fit in memory, then these become inefficient, and then you use gradient descent, which is what we're going to talk about primarily here. The main technique was used in most of the examples we talked about in most of the projects. So in gradient descent, you just choose some random parameters to start with, and then you move in the direction of the steepest descent. So you can calculate the slope. You find the steepest slope and you take a step to make it smaller. And since if it was a straight line, you'd get all the way to the bottom, but it's not a straight line, it's a curve, and you don't quite know the shape of the curve, so you take a step and then another step and another step. And this is what happens when we saw those epochs going up to like hundreds of epochs training a model. It's step, 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 trying to find the minimum. So there's an issue of the learning rate. How big are the steps? Well, if you make the learning rate small, you take small steps, and then it will take you a long time to get to the bottom. If the learning rate is too large, then you'll be skipping over the bottom and missing it, and then skipping over this and missing it, and skipping over this and missing it, and not getting close to the bottom. So it can be used on cell phone or signal band computers. Yes, absolutely. That's the big issue. Once you have done the training, actually running the model can often be done on a much smaller computer. So here's more pitfalls. If the function, these are called convex functions, where it's got one minimum and it monotonically rises on all sides from that minimum. That's nice, but sometimes you don't have a simple cost function like that. It has weird problems like this, like it has a local minimum that's not the global minimum, and it has plateau regions that are flat. And if it does, then you'll have problems. if you're up here, you might just spend a long time hopping on the plateau, not going anywhere. And here you might get stuck in the local minimum where you think this is the best, but it's not really the best. Both of these are problems in model fitting, and by the way, they're problems in the real world, problems like protein folding in particular. Proteins don't really fold to just one shape. There are other minima, so they fold into less perfect shapes for exactly this reason. So the mean squared error, one good thing about it is it's a convex function. There'll be no local minima. It's also a continuous function. It doesn't have any discontinuous spots, so it's well designed for this iterative process to work. Gradient descent, it has a nice property like it should where it's steeper out here and shallower only towards the bottom, and so if you just roll downhill like a ball, it'll work pretty well with mean squared error. It has a lot of desirable mathematical properties. This is why people usually prefer to use this error function. Another issue is feature scaling. You'll get the best convergence when the slope is about the same in all directions. If one of your parameters is scaled wrong, like it's 10 times bigger than the others, so it's like this, then you can end up taking a longer time to get there, sliding down a weird curve. So it makes your model work better if you rescale the features so they all have about the same size. And so now we can talk about how you put in the data. One thing about gradient descent, like I say, is you have to find the direction of the steepest slope. And the way you do that is you just calculate the derivative. Now, since it's a linear function, the derivative doesn't depend on the intercept. It just depends on all those slopes. So the derivative is just a summary of these parameters you put in there. So once you've chosen parameters, it's easy enough to figure out just from a similar equation, a similar linear equation that you might use to do one prediction, you do a similar linear equation to find the slope. So you know what direction is of steepest descent. So that's fine, it's very easy to calculate, but the problem is, to calculate this, you have to use the entire training data. You have to sum over every point, because of course every point contributes to the error, and so every point contributes to which direction will minimize the error. So, because of course moving closer to a point will make the error smaller, so you have to include all the points to see which points you're getting closer to and which points you're getting further from. And if you have a lot of points, this can be a burdensome calculation. So this is batch gradient descent. You take the whole batch, you calculate for each step, so on large training sets this will get very slow. It's going to scale linearly with the number of features. All right. Now, here's an example. If you have the learning rate too low, it will start here and then hop, 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 and it takes a whole lot of cycles to get the slope up to where it needs to be. If the learning rate is good, then you'll more quickly converge. If your learning rate is too high, it will take big jumps up here, and then a big jump down here, and a big jump up here, and you'll just get further and further away from the good answer because you have skipped over the good answer, and you're just wandering off around out here in the cold zone where everything is wrong. So that's an example of how you do still have to choose a good learning rate. All right, and so stochastic gradient descent is a crazy idea. I'm amazed it works at all. You decide that it's too much bother to calculate this slope using all the points, so you just take one point. You pick a random point and try to move closer to that one point. Then next time you choose a different random point and move closer to that point. That's what to smooth the slope. I'm surprised that would work at all, but apparently it does. Of course, it's much faster, especially with a huge training set. But it sounds stupid, and it's kind of random, and they show how it works. You're kind of randomly moving, and sometimes you're not even improving it because you just choose a point out here and move that way, but it does tend to converge to the bottom, they say. It doesn't ever really settle down and stay exactly in one place, but it does generally get you there, and it's much faster to do each calculation, so this can be the best pattern. And one thing about it is it tends to jump out of local minima because it has some randomness in it. So that somewhat works. Now, you have a learning schedule, and so what you might do is you might start with a big hop size, fast learning rate, and then slow it down, and then it will tend to settle down. And that's essentially what simulated annealing is. Annealing is a metallurgy concept. You've probably seen this in these martial arts movies. They make these swords, and they heat them up and pound them and cool them, and then heat them up and cool them, and go through many cycles of that to make the steel really strong. And what that does is you have the atoms sort of randomly jumbled, then you heat it up and all the atoms are moving a lot and you cool it, then you heat it again and cool it. And this, what you're trying to do is help the atoms settle down to their best position, like a regular crystal. You're trying to help them not get stuck in local minima where the atoms are disordered, but get them down to a really stable place to make the strongest metal. That's called annealing, and you can simulate it here in many of these models where you have a sort of random motion of things, and that's the temperature, and you heat things up by adding a lot of random motion, and then you gradually lower the random motion so they'll settle down. And that's what this does. So you start up here at essentially a high temperature, taking big steps, kind of randomly, and then you slowly decrease the step size, which would correspond to lowering the temperature, so that it will have less randomness, and then it will settle down to the answer here. So if you decrease the learning rate at a reasonable rate, then it will efficiently jump out of all the local minima and then efficiently settle down at the bottom. All right, now another issue is if your training set is sorted, like if you had all the zeros first and then all the ones and then all the twos and you used them in order, then of course this wouldn't work because your early steps would all be learning just from the zeros, then suddenly you'd be learning just from the ones and just from the twos, and you wouldn't really be learning how to fit the whole class. So if your data is not random, you should shuffle it. You can shuffle it before each epoch, or you can just pick the instance randomly. Instead of picking instance 1, 2, and 3, always just pick a random instance out of the whole family, so you don't have this problem of getting biased samples. All right, and this is the one that makes the most sense to me, mini batch, where you don't train it on one instance for every step, and you don't train it on the whole population for every step. You take a sample of the population. This is essentially what public opinion polls are. We're going to run an election and have all 230 million people vote, but before that we call like 1,000 people on the phone and ask them who they like. We take a sample, and from that sample we get a reasonable estimate of what the whole population will do. So you get a mini batch, and now you can get a performance boost. I got a typo here. You know, if your batch will fit into, say, your GPU and your memory nicely, then you can quickly do that calculation, and therefore it's going to be better than stochastic gradient descent where you're only taking one sample. You've got a larger sample, maybe 100 or 1,000 samples, so you get a better, estimate of the population. It makes a lot of sense. It might get stuck in local minima though, so that's nothing's ever perfect. And so here's an example of them being compared. Here's the stochastic, here's the batch one, where it learns from the whole model on every step, and that most efficiently, smoothly settles down to the right parameters. This is intercept and slope. So it settles down to the right parameter and stays there. Stochastic, where it, based on just one sample, jerks around a lot, but does eventually sort of settle down to the right region. And the mini batch is sort of in between. It's less erratic than the stochastic, and it approximates following the curve of the complete model, the batch model. How do we select the sample? Random, stratified, etc. Well, it's a good question, and I don't know a specific answer, but you're quite correct. Logically, the same things would apply as what we talked about last time. A random sample, if you don't know anything, but a stratified sample, I would imagine, would be better if you have reason to believe that one parameter is really important. I cannot have an authoritative statement, but I would think the same considerations we had last time would apply. All right. And so now, this is the part that really surprised me. What if you don't have a straight line? Which it seems to me like it would be very commonly the situation. Like, for example, the one we started up here, I already said I expected that. The very first one they gave here was happiness based on income. And I believe that this is not true. I believe happiness goes up really fast with income when you're very poor, and then slowly beyond that, and then probably even comes down for income beyond there. So I think this is not really a straight line at all, just from what I've read about it and stuff. So what if the model, if the data doesn't really fit a straight line at all, so putting a straight line through it is just never going to work very well. Very commonly, you need more complicated curves. And this, I thought, was wonderful. So you want to do a polynomial, square, cube, fourth order, then you can have more interesting curves. But you don't have to do the polynomial in the math. What you do is you just put the powers of the features as new features. So you now add, you create your data X, And then your model here is, this is quadratic data, so it's going to be half x squared plus x times 2 plus x plus 2. So this is a square, a parabola. So a straight line is not going to fit this data at all. Very well. Now what you do, you could try to fit a power law using the mean squared. And I used to do this analytically. I remember doing it for one of my first computer projects when I was like 17. It has been solved analytically, but the modern technique, which is really cool, is you now add another data array. So your original data will have, say, minus 0.7 is the first point. You add the square as another feature. Now you have two features, x and x squared. And now you fit a straight line through that. You have a parameter of x and a parameter of x squared. So the model is still fitting linearly. You've just fed in the square of the data as another measurement. This is quite brilliant. And that means you can use your same linear regression, and you're just modeling what parameter times x squared, what parameter times x, plus what parameter here. So you can use the same logic to do it, which is pretty brilliant. You have a linear regression through extended training data, and in science, this is where you take an example like you'd plot your thing on log paper and then put a straight line through it. And you could get paper that has squares in one dimension. So, you just move to a different piece of paper and you still fit a straight line, which means the amount of the techniques used in the computer to optimize the model can continue to be used, assuming things are linear, even when it's not really going to be linear to the real world measurement. So that's pretty brilliant. And let's try a Kahoot. I've got the Kahoots this week. In fact, I guess at the end, we'll do the Kahoots from last week. Let me get this. Okay. All right, this is 4A. What model does the large language model belong? That's a good question, and I don't know the answer. I assume it's linear, but I don't really know. I know the one essential ingredient is you resolve the words down to these tokens, and then I think you make a linear fit through the tokens, but I'm not really sure. It's a good question. Hopefully it'll become more clear as we go ahead. I would like to know more about it. I don't know the answer. Yeah, the transformers are important. The transformers are, you transform it to tokens, but then the question is, what do you fit to the tokens? What model? And I assume a linear model, but I really don't know. I don't even really know if they use gradient descent. I would like to know more. These are good questions. It's a classification model. Well, it makes predictions. That's why these are very good questions, and I would like to know. Hopefully, as the course progresses, we can learn enough concepts to understand what they're doing. I know they're doing a lot of fancy things. Based on frequency of words, yeah, it is. These are good questions. I don't know the answer. I see some intelligent ideas in the chat. Well, let's try this. All right, so which one uses a single calculation without iterating? The closed form equation, you don't even need a computer. That's been around forever. That's just what I used to do 50 years ago, around then. Yeah, anyway. All right. All right, so what training method uses only one instance in the training set for each step? Kind of amazing that it works at all. That's the stochastic gradient descent. You just take one sample. Doesn't seem certainly faster, but it seems outrageously sloppy. All right, what training method adds powers of features as new features? That's polynomial regression. All right, let me record the winners. All right, Greg and Woot. I think we know who Woot is from before. And Antignore. I think we know who that is too from previous classes. All right. All right. By the way, I should mention I'm not physically at City College. I tried doing that a few weeks and no students showed up and it's pretty uncomfortable and I'm building's locked and I really shouldn't be using it. So I decided to just make the Saturday class online only. So I'm working from home. So don't bother trying to come to campus on Saturdays for help, which nobody was doing anyway. I just wanted to be sure and mention that. So if you want help on Saturday, tune into the Twitch like this. Anyway, all right. So now let's talk about learning curves. The learning curve is just what we've had some simple examples of before, where you try to see how fast does it learn, how well does the learning work. So here, for example, if you have this data here, which I think is the quadratic data we made before, if you try to fit it with a line, that's 1 degree, and even the best fit line is pretty miserable. It's going to have a large irreducible error because it's not really fitting the data very well. Now, 2 degrees is the polynomial that will actually fit it very well. You could also fit it with 300 degrees, and then as you can see with all these parameters, it's going to try and jerk up and down to fit these exact data points, and that's overfitting because even though you'll get a lower error for the training data, it'll clearly be very wrong for the test data. And as I mentioned before, this is what happened to Donald Trump. He had a person who used an Excel line fitting program and took the COVID data and predicted it will just go to 0 in by Easter, in a month or so from the time and he said, there, it'll all be gone by Easter, based on this model. They had a model like this that was overfit, that jumped all over the place, and so he had something like here, it's going to go to 0, right here. That's what he had, some kind of model like that through whatever data they had. It wasn't Jared Kushner, it was another guy less famous who was an accountant, who just knew how to use Excel. And he just took the COVID death or COVID hospitalization data and then just put it in Excel and fit like the default model, and it just didn't know enough to recognize this problem, so it just showed it going to 0, and Trump said, it's just going to go to 0, don't bother, everything will be fine. Anyway, all right, so you could try to evaluate these with cross-validation like we did before, training them on part of the set and testing them on another, but there's another way, which is a learning curve. You plot the training error and the validation error as a function of iteration, and then you watch to see how they change. Now, if you cannot train it incrementally, then you just use gradually larger subsets of the training data to get a measure of how getting more data will improve it, and then you have training set size here. So if you train it on a really small set, then the line can fit it. If you only have 1 or 2 instances, it can draw a line through it, but when you start having more than 2 points, the line can't fit it anymore, and you rapidly settle at this large steady error because you've managed to draw this line, which gets as close as you can get, and you can't get the error below that level with the line. So the line will end up here, and testing out in the validation data, you'll just get the same value because the problem is you have the wrong curve. You've got a stable result as close as you can get, but it's not very close. You have a high error, and it rapidly plateaus and stops improving. Now, if you have overfitting, then you train it down here, and your training error goes down and down, and your validation error is staying here, so this is these overfit areas where your training error is low, but your validation error is high because you have fit the random variation of the training data and it's not really reflective of the population as a whole. Now, one cure, of course, is to use less parameters or moderate it so it cannot use extreme values. But another cure is just add enough data. And you may remember a statement that came by last week or the week before where they said studies have shown that it doesn't even matter what training method you use as long as you have a lot of data. If you have a whole lot of data, that will compensate pretty much for any training method. And you can see that here. You could even continue to use like a 10th degree model to fit this second degree curve, and it will eventually get right when you have enough data. It will just presumably turn all the parameters to 0 that have a power greater than 2. And it'll eventually learn that, even if you didn't add that in the first place. Can we use two curves, one for the upper and one for the lower, to surround the blue dots? Yes. That's another way. That's what people do in science. They have like error bars. So you conclude it's here or could be out down to there or another. And if you look at the, there's another model like that where you try to separate two classes in a categorization and you try to get the widest possible road separating between them. So those issues do come up. But you're right, that in science you would fit a curve like this, and then you would say I have an error like this much, and then you'd have an upper bound and a lower bound, and say we have like a 90% confidence that it's between here and there. That's the kind of thing you would do. All right. So there's an example of overfitting, and one solution for overfitting is just add a lot more data. All right, so here's the types of error. Bias is caused by wrong assumptions or underfitting where you're using a model that's just not going to fit. So you're never going to get the error down too far because your model is just not a good fit. Then there's variance. This is overfitting where you have too many parameters. So your training error will be low, but your validation error will be high. And then there's irreducible error. That's the actual noise in the data. No model can ever defeat that, except of course the ridiculous one with too much overfitting that's actually fitting the noise. So if you increase a model's complexity, then you increase variance and reduce bias. You're more likely to actually, if you have more parameters, then you're more able to fit the actual shape of the data, but you're also at risk to accidentally fit the noise too. All right. So we'll talk about regularization, which is the way you overcome overfitting. So you regularize the model. One simple way is just lower the number of polynomial degrees. That's one way to regularize it. For a linear model, you constrain the weights of the model, and there are three ways to do it: ridge, lasso, and elastic net. And these are just ways to restrict the parameters so they can't get too extreme. So the ridge regression is extremely simple. You take the mean squared error of all the points, and then you just take the mean squared parameters. You just take the parameter itself and square it and add it up. So you're just going to punish you for using large slopes to try to make you fit the model with low slopes. That's all there is to it. And you have a hyperparameter alpha, which determines how much of this regularization is going on. So if alpha is 0, you just have linear regression with mean squared error. And if alpha gets really high, then all the weights get really small. And you're just going to fit the model with a single static value horizontally there. So this is called the L2 norm, using the square of the weights. So here's various levels of ridge regularization. With alpha 0, it's going to fit the best straight line through these points it can, and there it is. If your alpha is 10, it's going to lower the slope, try to fit with a lower slope. And if alpha is 100, it's going to basically fit just a constant value with a slope of 0 hitting the middle point. And here is, I think, a polynomial. So the with alpha equals 0, you get this really wavy polynomial through the data. And as you regularize it more and more, it smooths out. It lowers these parameters so you get a more smooth curve through the data. And you can see how I don't believe this blue curve is really following the data correctly. I think it's just being deceived by the noise. And the green curve, I think the red curve is actually the best to reflect the real trend of this data. And that's with a higher value of alpha. So the regularization is just like sanity. I remember doing this intuitively as a scientist. When I would just measure things like this, I would just decide whether to fit a line through it. I would not fit this wavy thing through it. I would just say, well, it's probably just growing as this grows, so I'll put a line through it, or maybe an exponential or parabola or something. So without having a mathematical formulation, I would just intuitively try to choose a curve that fits it. And then, of course, when you can, you try to make more measurements or improve your equipment to get rid of some of this noise and see what the truth is. But especially for expensive things like particle accelerator experiments, you really can't do much better experiments. You just have to try and squeeze all the information you can out of the data you have. All right, so LASSO actually stands for Least Absolute Shrinkage and Selection Operator Regression, which is a ridiculously complicated name for a very simple concept. Instead of using the square of the parameters, you just use the absolute value of the parameters and add it to the error bar. So it's going to accomplish essentially the same thing as the last one. It's going to just prefer lower parameters, lower slopes, but tends to eliminate. What it does is it tends to eliminate the weights of the least important features. So, and again, the same thing is here. So here's a straight line being put through these curves with alpha 0. That's linear regression. And here it is with some moderation and some more moderation, where it just puts a horizontal line through the average. And here's the same thing for this one. There's that curvy thing you get putting a polynomial through it. And with some regularization, you get a good one. And with too much regularization, you just get a flat line. So they both accomplish essentially the same thing. All right, and then elastic net is just in combining both to get them out. You have take the mean squared error, and then you add the absolute value of the parameters, and then you add the square of the parameters. And you have a parameter r that determines how much you weight those. So you consider both possible additional costs, both favoring lower parameters. So it just regularizes it and smooths it. It's the middle ground, and therefore it's using both the L1 and the L2 norms. I was very pleased to learn these terms because I saw them in the Python models we were making. You had L2 and L2 parameters, L1 and L2 parameters to set, and I didn't know what they were. I played with them, but I wasn't sure what they mean. Now I know. The L1 parameter adds the first power of the parameters as a moderation, and the L2 parameter adds the squares of the parameters to the error as a moderation feature. And they both do approximately the same thing. So you can do linear regression without regularization. In practice, this is usually a bad choice. Usually some degree of regularization will improve your model's ability to fit the actual underlying phenomenon and not be distracted by the noise. Ridge regression is, they say, a good default, which I would imagine, just at a guess, I think keeping the square is usually the best. This is an old rule from centuries ago. The mathematicians figured out that minimizing the squared error is something very easy to do. And it fits with sort of a Gaussian model of what noise is like. And in general, the squared error is probably the best measure, all things being equal. But if you think that only a few features are useful and a bunch of the features you measured are in fact irrelevant, then LASSO or ElasticNet might be better because it will try to move a lot of parameters to 0, and that might be right. Remember that California housing data where we showed there were like 10 measurements of the people that lived in a region of California, and you're trying to predict the housing price, and it turned out that really only like 2 or 3 of those features actually mattered. So something like the LASSO or ElasticNet might be a wise decision there. Anyway, ElasticNet is recommended over LASSO, obviously, because LASSO can behave erratically. And anyway, so these are, that's the one. So here's another way to do it. This is called the cheap way. You just do gradient descent, and as soon as it starts getting worse, you just stop. This is what I remember. I commented in practice. You could see this happen with some of the models we were running. It gets smaller, 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 and as soon as it gets bigger, it just stops. So this is one way to get there. Rather than adding some regularization thing, this is a way to get there on the training set and the validation set. That's one way to do it. All right, and then there's this thing called logistic regression. We're trying to, now the algorithms we've talked about before are for curve fitting. So they're predicting a y from an x. But suppose you want to do classification. You want to sort things into categories like 1, 2, and 3. That's not really curve fitting, but you can do it with a regression algorithm. You run the regression algorithm and you get an output y, and then you just take that y and subject it to a threshold. So you get a number, which is your percentage probability that an email is spam, and then you decide if that's greater than 50%, call it spam, and if less than 50%, call it not spam. The early stop assume global minimum. Yes, and ignore. Absolutely. That's the point. That early just stopping as soon as it goes up would clearly be subject to falling into a local minimum. So you're quite correct. It's that would be a weakness of that technique. All right. And so they call this the logistic function. You have a function you're measuring here, And if it's just below a certain level, below 50, you call this false, and above 50, you call this true. And there's a lot of things like this. Like I used to do human vision perception. And if you're trying to see a dim light, then if the light is below a certain level, you can't see it, and above a certain level, you can see it. So you have a thing like this. All right, so you define a cost function of a single training instance. This is the probability it puts out. So if the probability is near zero, if the model has a low probability for a positive instance, so if you have a true condition and it makes the error of having that below 50%, then you have a low probability in the top row, and that's going to be a high cost, because say that if the probability is say 10%, this would be the log of 1/10, which is a big negative number, and that makes it positive. So this will give you a high error for false negatives, where it's actually true but you thought it was false, and this is the opposite. If it was actually false but you called it true, so p was up near 1, then again you have a high cost. So this is a way to create a cost function of a single training instance for a classification task, where you're classifying it as true or false, and you know the right answer, whether it should be true or false. So that's the logarithmic cost function. And it turns out that there's no closed form solution for this. I mentioned many times the mean squared error is a nice simple one, and there are analytical ways to solve that that date from before the days of computers. This one does not have a closed form solution, but the cost function is convex. There won't be any local minima, so gradient descent will work well. And here's a famous problem. I've done this one years ago, even before I knew any of these modern algorithms. This is a very famous problem. Somebody that studied flowers decided to sort irises into the 3 species. For some reason, I don't know anything about irises, but apparently there's 3 kinds of irises: Virginica, versicolor, and setosa. And he decided to see if you can tell the irises apart by measuring the petal length and width and the sepal width, which I think is between this dark color and the edge, something like that. So you make 3 length measurements of the flower and then see if you can sort it into categories. So here's a well-known famous data set here for machine learners to use. It just consists of this. You have the right category. I think that's what this is. I'm not sure, but you do know the correct category. And you have sepal length, sepal width, petal length, and petal width. Those are the parameters. And we're going to use these 3 parameters: sepal width, petal length, and petal width, to try to predict it. So here's the data. You have ones that are Iris virginica, and they're here. And then you have ones that are the other 2 down here. And we're just doing a yes or no model. So we're not going to discriminate between these 2. We're just going to do Iris virginica or not Iris virginica. So here's some data. And you'll see if you just look at petal width alone, that was pretty good. It'll detect all these correctly. Petal width below a certain number is not Iris virginica, and above a certain number it is. But here's some overlap between the 2, so there's going to be some error if you use petal width alone as your measure. And if you use petal length and petal width, then you have length this way and width there, and here's the data. Here's the ones that are not Iris virginica, and here's the Iris virginica. And you can see now the best fit is a line like this. The dashed line is the best fit with 50% probability. And this is relating to the question earlier. Here's what you'd have: 75% probability, and someplace around here is 25%, and here's 90% and 15%. So that's what you do here. You'd say things above this line have a 90% chance of being Iris virginica. Things above this line have a 50% chance of being Iris virginica, and so on. So you can have these various different measurements. Sort of thing you'll get. All right. So let's try another Kahoot. 4B. All right, let's give it a shot. All right, so which error do you get when you do overfitting? That's variance, they call it. All right. You're trying to put the wrong shape through the model, like a line through a parabola. Oh, excuse me. That's where you overfitting is where you're putting too high a degree polynomial through, so it's following the noise and not just the trend. All right, which method uses L1 and L2 norms? That's elastic net regression. It uses both kinds of moderation. Both the absolute value of the parameters and the square of the parameters are added to cause it to favor lower parameter values. And which method uses the absolute value of the errors instead of the square? That's lasso regression. It occurred to me I should have said the absolute value of the parameters, I guess. Well, let me go back. I make sure I'm not fouling this up. Let's go back and look at lasso. I think that was for, yeah, lasso regression. Yeah, you still use the mean squared error, but you use the absolute value of the parameters. So my question is phrased a little badly. All right, anyway, this lasso regression. All right. All right. And Boots won twice. Good. And Ant Ignore has won twice. All right. Fair enough. I'm going to stop this video.